So this is the most important section in calculus 2. So this is what we call the integration by parts formula. So this is integration by parts. So in short, this call is IBP, integration by parts. So I see very important. Very important. So what we're gonna do, we're gonna categorize these problems into several different types, and then we try to remember by type. So that is the kind of best way to learn this technique. So we might do like little bit more examples here. So before we do, let's try to kind of understand why we need a new technique. Okay, so let's start with this one. So let's say example, let's say integrate e to the 2x dx. So if I say integrate e to the 2x dx, this is very easy to integrate. Remember, we had a formula. So what the formula says, if we have e to the kx dx, the integral is 1 over k e to the kx plus c. So you divide simply by k. That means according to that formula, this is simply 1/2 e to the 2x plus c. Okay, so that means we can do it. Let's look at another problem. So how about this one? Let's say integrate x e x squared plus 1 dx. What do you think? If we have x e to the x squared plus 1 dx, can we do it? And you can see that from the four formulas, this is like e to a function and its derivative situation. For example, you can write this one as 1/2 2x e to the x squared plus 1. Then from the four formula, you can write the answer. So what is that? Is 1/2. So since we see the derivative, answer is e to the x squared plus 1 plus c from the formula. Or you do this using substitution method. You can pick u equal x squared plus 1, and then du equal 2x dx, and you can see x dx is there, so you can multiply and divide by 2, and then you have everything you need. You can do that, or you can use the four formulas. Okay, so this is from the four formulas. So I'm gonna call it FF. Okay, when you say FF, that means the four formula. So from the four formulas, you can directly write the answer. Okay, that's fine. Let's look at one more example. So if you look at this example, let's say I'm going to make the problem little looks easier. So we have x e to the x squared plus 1. Instead, let's say x e to the x dx. How about that? Now you can see that x is, if you consider x as a function, so e to the x, but the derivative of x is 1. It's not x. So that means we cannot use the four formulas here. Okay, so the four formula does not work because that's not the derivative, and you pretty much see that none of them work. Okay, none of the technique that we already know doesn't work here. So that means there's a question now. So that means we need a new technique. Need a new technique. Need a new technique. So what is the new technique? The new technique is what we call the integration by parts formula. Integration by parts formula. Integration by parts formula. Okay, so let's derive the formula, and this we get as a result of the product rule. Okay, so this is a result of the product rule. Okay, so let's look at the product rule and try to derive the formula. So let's derive the formula. So IBP formula, integration by parts formula. So what do you do? Let's say you have two differentiable functions, and then we try to consider the product of that. So d by dx. So let's say we have a product fx and gx. So if you have a product fx and gx, what's going to happen? So so what's the product? So it is the f prime x gx plus g prime x fx, right? F prime x gx plus plus g prime f fx, g prime x fx. So that's the product rule. So now what we're going to do, we're going to move the terms around. So I'm going to write from this one, we can say fx g prime x is equals to fx g prime x equals to d over dx fx gx minus we have gx f prime x. Okay, so what I do, I'm going to solve for so I'm going to move this term, I'm going to solve for this term. So fx g prime x equal the derivative of the product minus the other term. Now what we're going to do, we're going to integrate both sides. So if you integrate both sides, you're going to get fx g prime x dx, and then what we do, we can integrate the derivative fx gx dx, and then minus, we can integrate this one as well. We can integrate this one as well. So you're gonna get f prime x dx. Okay, so what we do, we integrate. So and then you can see that here integral and the derivative get cancel each other. So that means you end up getting fx g prime x dx equal, once they cancel each other, you're going to get fx gx minus gx f prime x dx. So we kind of have a formula here. So what's going to happen, you can see they switch the derivatives. You see that? Here we have the derivative of g prime x, here we have derivative of f prime x. So they switch the two. So what's going to happen? So the idea is, maybe this integral is difficult to integrate. Okay, difficult. So what we're trying to do, we try to transform the difficult integral to a easy one. So that's the goal. So we transform a difficult integral to an easy integral. How we do it? We pick fx wisely. Okay, so pick fx wisely. So that's the idea. Okay, so once you pick fx properly, so we pick fx properly so that you get a easy integral compared to the original integral. So that's the kind of idea going behind. So you transform a difficult integral into a easy integral. Okay, so and then so let's try to actually get to the formula. So what we try to do, we're gonna make some substitution. We're gonna say let u equal fx and v equal gx. That's what we do. So if you do that, what's going to happen? So if you take the derivative from that, you're going to get du equal f prime x dx, dv equal g prime x dx. Is that right? Du equal f prime x dx, dv equal g prime x dx as a substitution method. Now what we can do, we can substitute. So that means, if you look at the formula, this part simply becomes u, this parts become dv, you see that, and this is u, this is v, and this is v, f prime x dx is du. So that means your integration by parts formula now becomes, so I'm going to write the new formula, so it's going to be u dv so it is simply u dv equal uv minus v du, right? u dv equal uv minus v du integral. So this is what we call the integration by parts formula. Okay, integration by parts formula. So I'm called star. So this is what we sometimes call IBP, integration by parts formula. Okay, so u dv equal uv minus v du, u dv equal uv minus v du. So but you can see that it's simply coming from the product rule. So now what we can do, so the goal is to pick u properly. Okay, so you try to pick u properly, and then very easy to do the integrals. Okay, so because what we're trying to do, we're going to transform a difficult one into an easy one. So that's the goal. You start with a difficult integral and you can transform it to easy integral by properly selecting fx. So so let's do a couple of examples. So how about this one? So what I'm going to do now is do several examples. Okay, so that's the only formula, just only one formula. So let's see. Yeah, so the whole section, so this is what we call the most important section of the whole calc 2. Okay, so let's do first example. So before I do, I'm going to give you a trick. So we're going to go with notes. So the first note, because the problem is how to select these. So there are some guides that I came up with. I don't know whether these are in books. So so the first guide, when we have okay, so again, so the question is, we have u dv equal uv minus v du. So the question is how to select u. So that's the question. Okay, so the question is how to select u. Okay, so that's the question, how to select u, so that the v du is easy to integrate. Okay, easy to integrate. So that's the kind of idea, how to select u so that v du is easy to integrate. So there are some tricks. So the first tip is, when you have polynomials and trig functions, so that's the first type. We're gonna pick u as the polynomial. Okay, that's the first trick. When you have polynomials and trig functions, we're gonna pick the polynomial as u. Okay, we're gonna pick the polynomial as u. So let's do, that's the first one, that's the first trick. When you have polynomials and trig functions, pick the polynomial as u. So let's do one example like that. So the example, so let's integrate x sine x dx. So for this kind of problems, we need 4 things. So because what are the 4 things? So according to our argument, you know that so this is, so when you have a trig function and a polynomial, we're going to pick the polynomial part as u. So that's the u. If this is u, the rest is dv. That's what the formula says, u dv. So and then the rest of the formula, it simply becomes uv minus v du. Okay, So there are four things here. What are the four things? U dv and v du. So what we're trying to do, we're going to find them. Okay, so we're going to start with u. So u equal x, and the dv is the rest. So dv is rest of the integral, that is sine x dx. So that's the starting point. And what we do after we write these two, you're gonna take the derivative of the first one. So that means du over dx equal 1. If you cross multiply, you can write this one as du equal dx. So we take the derivative of the first one, integral of the second one. We're gonna integrate. So we're gonna integrate. So it's a dv, integral of the second one, derivative of the first one, integral of the second one. That's what we do. Okay. So and then if you integrate this, v, integral of sine is negative cosine x. We do not add plus c here. We do not add that. Okay, that's very important. That we just add at the end. So we need four things. So what are the four things? So there are always four things. 1, 2 that we start with, and then we have 3 and 4. So we always need these four things in the integration by parts formula. So we normally do that calculation before we go to the formula. So there are four things. You start with u and dv. First one you take the derivative, second one you take the integral. So now we have everything we need. Now we can go back and substitute here. So let's substitute. So what is u? U equal x. What is v? Negative cosine. So I put the negative sign in front. So negative cosine minus, and then v, that's again negative cosine. What is du equals to? Du equals to dx. So du equal to dx. Now if you simplify this a little bit, negative cosine x, negative sign you can take out, you have cosine x dx. So this is very easy. So you see that you transform the difficult integral into a easy one. See, this is easy. Yeah, that's easy. That's the whole point. You transform a difficult integral to an easy one. Now you're gonna finish the integral, rest of the integral. So this is already done. So x cosine x, you don't have to do anything here. And then what's the integral of cosine? Sine. So right, sine x. Now you add the c here. So plus c. So that means, so that's the answer. Okay, that's the answer. So now you can see that if you take the derivative, so let's verify this one whether this is true. So what I'm going to do, I'm going to verify, but you don't have to do that always, but let's just do one example. So verify whether your answer is right. So verify. So let's take the derivative of this one. So negative x cosine x plus sine x plus c. So what do you get? So for the first one, you have to use the product rule. So if you use the product rule, take the derivative of the first one. So it's negative 1 cosine x plus, actually it's a minus, minus negative x, and take the derivative of the other one, so it's a negative sine x, and then take the derivative of cosine sine x, so it's a cosine x plus 0. And you can see that this and that get cancels, so you simply end up with negative positive x sine x as expected. Okay, because if you take the derivative, you get x sine x back, so that means that's true. Okay, that's true. So yeah, so let's do more examples just to idea. So again, so what's the trick was, if we have a polynomial and a trig function, we pick u as the polynomial part. Okay, we pick u as the polynomial part. So that's exactly what we did here. So we pick that one as the u. Selecting u is the difficult part. Okay, and you need to remember certain things. So let's do one more. How about this one? So example, integral of x cosine x. And again, so what we do is a polynomial and a trigonometric function. So u equal x, and then the rest. So this is u, and the rest of the integral is dv. So that means dv equal rest, so it is cosine x dx. Take the derivative, so du equal dx. Take the integral, so if you take the integral of cosine, is sine x. So right, integral of cosine is sine x. Yeah, good. So we have all the four things here. So let's substitute. So it is, so the formula is uv minus v du, and the u is x, so it's x sine x, minus v means sine x, dx equals to du equals to dx. This is easy integral, so that means x sine x, minus what's the integral of sine x? Integral of sine x is this integral. So sine x is negative cosine x plus c. So that means you're gonna get x sine x plus cosine x plus c. Okay, how about another problem? So how about if you have a x squared term here, x squared cosine x dx. Again, polynomial geometric function. So we're gonna do u equal the polynomial part, and then dv equal cosine x dx. Take the derivative, so du equal 2x dx. Here the integral, so it is sine x. We have all four here, so we're going to plug in. So again, this is u and this is v, right? So it is uv minus v du. We're going to plug in, so it is x squared sine x minus v is sine x. What is du? Du is 2x dx. So that means if you rewrite it, x squared sine x minus, you can take 2 out, you get x sine x dx. Now what do you do? You have to do this again. See that? But it's simpler than the original one. In the original one you had x squared, now it is only x. So what do? You do this again. You again pick u equal x and dv equal the rest, that means sine x dx, and then we do du equal dx, and v equal negative cosine x, and then do that again. But since we did this earlier, we don't have to do it again. But normally what we do is we do this again. Okay, we do this again, and then we're going to substitute for that. So let's say, so since we did this earlier, we can substitute. So what happened? So it's x squared sine x minus 2. So we're going to substitute. What is x sine x dx from the? So we can go back and see what we happen. So x sine x dx, we did that earlier. So x sine x dx is negative x cosine plus sine x. Okay, negative x cosine x plus sine x. So we can do that. So it is negative x cosine x plus sine x, and then just say plus c. We don't need negative c, it's just a c. Okay, so that means if you multiply through, you're gonna get x squared sine x plus 2x cosine x minus 2 sine x plus c. So that's the answer. So so what we normally do is you do that again and then substitute, and then substitute for that. But since we already did x sine x, so we can substitute here. Okay, so that's the first type. So we have a polynomial and trigonometric function. Let's go to the second type. So what's the second type? So the second type is so what we have is we have polynomial and exponential function, polynomial and exponential function like ex, e to the negative 3x, stuff like that. Okay, so yeah, and so if you have this, what we're gonna do here again, we're gonna pick u equal polynomial. Okay, u equal polynomial. So this is similar to trigonometric functions. So when you have trigonometric function and a polynomial, we're gonna pick the polynomial. When you have polynomial and a exponential function, we again pick the polynomial part as u. So let's do the problem. Remember, we had a problem that we could not do earlier. Now probably we can do it. So what was that? Integrate x ex dx, right? X ex dx. Okay, so according to this argument, so what we're trying to do, we're going to pick the polynomial part as u, the rest as dv. So that means we have u equal x, dv equal ex dx. So if you take the derivative, it is du equal dx. If you take the integral, v equal ex. So let's plug in. So it is uv minus v du. So if you plug in here uv, so it is x ex uv minus v, that means ex, v du. What is du? Du equal dx. Okay, you can see that this integral is easier than the original one. Okay, so we're gonna finish it. So we're gonna get x ex minus ex plus c. Okay, so that's the answer. And you can see that if you take the derivative of this one, you're gonna get that one back. So you can see it's not that bad, but we can do this without this technique. Okay, so that's why this method is really powerful, because you can do a lot of problems that you cannot do normally. Okay, so I'm going to give you an exercise for you to try. So this is an exercise. So exercise is integrate x squared ex dx. Okay, so you might need to do 2 steps, because if you do the first step, it's gonna bring x squared to x, and then you do it again from x ex, and then you plug in and simplify, so you're gonna get the answer. Okay, so you can try this. This is similar to the problem that we did earlier, problem with sine with x squared, so the same thing. Okay, let's do one more example. How about this one? So example t e to the negative t dt. Okay. Again, what is u? U equal the polynomial part. The rest gonna go as dv. So it's a negative t dt as dv. So so this is u, this is dv, everything else. Okay, and then you can the first one you're going to take derivative, so du equal dt. So du equal dt, and then here we take the integral, we're going to get v equal it is a k equal -1, so it is negative e to the negative t. Okay, certificate. Okay, so we have everything we need. So let's plug in there. So it's uv minus v du. So uv, that means negative t e to the negative t minus v du. V is negative e negative t, du equal dt. And this is a easy integral, so it's a negative t e to the negative t, negative positive e to the negative t dt. This one very easy to integrate, so you're going to get negative t e to the negative t, negative e to the negative t plus c. Okay, so that's the answer. And I'm going to give you another exercise, so why don't you try this one. So this is we can say x e to the negative 2x dx. Okay, you can try this, and please try these problems and send me through an email. I'm gonna collecting those things as extra credit problems and will be useful at the end of the course. Okay, so I'm gonna collect them. I'm gonna give you some point for this, and so this is gonna be useful. Okay, so we will discuss two types. The first type is you have polynomial and exponential, polynomial and trig function, and then the second type is we have polynomial and exponential functions. In those both cases, we're gonna pick u equal the polynomial. So let's go to the third type. Okay, let's go to the third type and see whether the same trick gonna work or not. So so the third type, so number 3, when we have polynomials and log functions, ln functions, okay, some ln functions, what we're gonna do, you're gonna pick u as the ln function. So you see this is the first one, because the thing is that if you try to pick the polynomial as the u, then what's going to happen is you're going to get the log function, but you have to integrate and you're going to get stuck with that most of the time. So that means we are not going to use that. So if you have a ln function, we're going to pick the ln function as u. Okay, so let's do a problem like this. So this is the first example of this type. So we have let's say just ln x dx. How about that? Just ln x dx. Okay, so you can see that we cannot integrate this one using any of the method you know so far. Okay, so none of the method works. None of the method works. So you kind of get stuck here. So so how we do it? So what we're trying to do is we're going to use the new trick here. So what's the method we have? We says that, so if you have a log function along with some polynomial, see the polynomial is simply 1, what we normally do is you pick the log function, so u equal ln x, that you need to remember. Okay, and then the rest, so dv, which is simply the rest of the function is dx. Okay, so you take the derivative. If you take the derivative, what do you get? What is du by dx? Which is 1 over x, remember? So that means du equal 1 over x dx. If you integrate here, v equal x. So we have everything we need. We have all 4. Okay, so we have 1, 2, 3, and 4. Okay, all 4. So let's plug in. So if you plug in du v minus v du, so so we have everything we need. So uv, that means the product of the two, so it's x ln x, the product of the two, minus v. What is v? V is x. What is du? 1 over x dx. You can see there is a really nice cancellation going on here, and that is the reason why we pick u equal ln x, because when you take the derivative of that, it's going to be just 1 over x, so it's going to be simple. Okay, so that means you simplify this a little bit, you end up getting x ln x minus dx. That means if you integrate that, you get x ln x minus x plus c. Okay, yeah. So maybe let's do one more. So how about this one? Let's say x square root ln x dx. Okay, so according to theory, we know that if we have polynomials and log function, we're going to pick the ln as the u function. So I'm going to rewrite this one as ln x square root x dx. Okay, so then we know everything we need. So so what we have is, that is the u function, that is the u function, that is the dv function. Okay, so that means u equal ln x, dv equal x to the 1/2 dx, so du equal 1 over x dx. v equal integrate is very easy, it's 2/3 x to the 3/2. Okay, so we have everything we need, so we're going to plug in here uv minus v du. uv, what is uv? uv means the product, so it's a 2/3 x 3/2 ln x minus v 2/3 x 3/2 du equal 1 over x dx. You can see this, there's a nice simplification here, so you're gonna have 2/3 x 3/2 ln x minus 2/3. If you simplify, you're gonna get x 1/2 dx. Now you can integrate that one again, so so that means you're gonna get 2/3 x 3/2 ln x minus, if you integrate this one, you're gonna get another 2/3 x to 3/2, so that means a 4/9 x to the 3/2 plus c. You add the c at the end. Okay, so that is the answer for that. Good. So we already talk about 3 types. Okay, so we have polynomials and trig functions. We're going to pick the polynomial. We have polynomials and exponential functions. We again get the polynomial. But we have polynomials and log functions. If you have polynomials and log functions, we're going to pick the polynomial. We're going to pick the ln function as the as u. Okay, so let's talk about definite integrals. Okay, so so how about if you have a definite integrals? So definite integrals. Integrals. So what's going to happen if you have a definite integral? We again use the same formula. So that means if we have fx g prime x dx, the integral going from a to b, which is fx gx, and then integrate b to a minus a to b gx f prime x. You can see that, just substitute the values, that's it. So that means if you do the other way, it is u dv, so we're going to have the limits ab equal uv, again the limits minus v du, have the limits. Okay, so what do you do after you integrate? You're going to put the limits. Okay, so after you integrate, you're going to put the limits. Okay, so I'm going to combine this with a problem from like another type. Okay, so we do the definite integral and the next type. So what's the next type? So number 4. So the next type, when we have inverse trig function, we're gonna pick that as u. So the inverse trig. Okay, so that's the next one. When you see inverse trig, we're gonna pick that one as the as u. So that's the fourth type. So let's do a problem from that. So let's say next example, integrate tan inverse x dx. Let's also make it definite integral. So it is 0 to 1 maybe. Okay, so let's see. So what the theory says? So the theory says when you have definite integral, pick that one as the as u. So tan inverse x as u, and then we have the dv, that's the rest, in this case dx. So v equal x. So that is easy. Take the derivative. What's the derivative of tan inverse x? Derivative of tan inverse x is 1 over x squared plus 1. So that means du is 1 over x squared plus 1 times dx. So we have everything we need. Okay, everything we need. What we remember is when you have a trig function, we're gonna pick that one as u. Okay, so let's finish the rest of the integral. So it is uv minus v du. So uv, what is uv? X tan inverse x. So you're going to plug in 1 and 0. Remember, these values are now all radian. Okay, all radian. And then minus integral 0 to 1 for the same limit. What we have here, v du. V means x, du means x squared plus 1 dx. First, let's plug in the values. If you plug in 1, so you're going to get 1 tan inverse 1 minus we have 0 tan inverse 0, and then minus, this is 0 to 1 x squared plus 1 dx. How much tan inverse 1? Tan inverse 1 is pi over 4. So this is pi over 4 minus tan inverse 0 is 0. So it's going to go away. So here you can see that this is x over x squared plus 1. So this is coming from 4 formulas, remember? So you see the derivative on top. So what's the derivative at the bottom? Is 2x. So that means we can write this one as 1 half 0 1 2x x squared plus 1. Then this is simply the natural log. So that means this is pi over 4 minus 1 half ln x squared plus 1, and then we have 1 and a 0. So what's going to happen is pi over 4 minus 1 half. So if you plug in 1, you're gonna get ln 2 minus, if you plug in 0, ln 1, but we know that ln 1 is 0. So that means this simply going to be pi over 4 minus 1 half ln 2. Okay, so that's the final answer. So you can see that this is not that bad, and also if you want, you can bring the 1 half inside as square root, but also you can leave it like that. So there's no like final version of that. So some people prefer this way. Yeah. So but look at this problem. Okay, so you can see that what's gonna happen, you're gonna plug in the values after you're done. So for the uv, you can directly plug in the values. For the other one, it just become another definite integral. So you just do it the way you create definite integrals. Okay, so this is not that difficult, but you still need to practice this a little bit. So what do you want to remember? So when you have definite integrals, it just you treat this one as the same way as the indefinite integral, but after you finish the integral, you're going to substitute the values. Okay, you're going to substitute the values for the uv. For the other one, you simply complete the integral. Okay, So that's about that. So we did the inverse integrals, inverse trig functions. If you have inverse trig function, you're gonna pick that one as u. Okay, so so I'm gonna let you try this one. So this is the third extra credit problem. So remember, the all three extra credit problems, do it as one problem. So so what's the next one? Is this one. So it is extra credit problem. I'm going to say EC, extra credit problem. So what is that? Evaluate so let's say x sine inverse x sine inverse x dx. Okay, so tell me what you get for that. So that's the third problem. So I already gave two problems, so this is the third problem, x sine inverse x dx. Okay, so remember, send all three in one problem, okay, as just one. Okay, so that's about that. I'm gonna do just one more example from a different type. So this is the last one. So this is I should say number 5th. Okay, the 5th type. So what's the 5th type? When you have both exponential and trig. Okay, and trig. So if you have exponential and trig, now there's a problem, you know, which one you're gonna pick. So normally when you have exponential and trig both, we normally go with u equal ex. Okay, so this is the kind of thing we do, but even if you switch the order, you can still do it. So this one you can pick anything you like, but normally we're gonna go with the exponential function. Okay, so let's try to do one last problem and see how things gonna go. So this is like a special problem. This is useful in many situations. So how about this one? So integrate e to the x, let's say sine x dx, sine x dx. Something like that. Okay, so so what we trying to do is so as we normally do, we're gonna pick as we say, we're gonna pick u equal ex. So dv equal sine x dx, and take the derivative. So du equal ex dx, and then v equal this is the integral, so negative cosine x. Now let's plug in. So it is uv minus v du. So what's gonna happen if you plug in? So you're gonna get negative negative ex cosine x, and then once you plug in there, you become plus you're gonna get ex cosine x. So what happened? So you start with this integral and you end up with the other integral. So you switch. So you have ex sine x, now it becomes ex cosine x. So it didn't make it simpler. Okay, so just switch. So what do you do now? We're gonna integrate that one again. Okay, so yeah, it's kind of weird. So well, let's do it. So we're gonna do that one now. So what do you do? Ex, this is like special trick, cosine x dx. Now we do this one. So again, now what we can do? U equal ex again, dv equal now cosine x dx. So that means if you take the derivative, you get du equal ex dx, v equal cosine, that means sine x dx, just sine x. So let's plug in. So uv, that means ex sine x, and then minus v du. What is v? V is sine x, du is ex dx, so that means ex sine x dx. So right, ex sine x dx. So what happened? So when you do ex cosine x dx, what happened? It becomes sine. Now what we're gonna do? We're gonna substitute that into the previous one. We're gonna substitute that in the previous one. So let's substitute. So substitute. Okay, substitute. So what do? You start with this. So it is ex this is the original one, ex sine x dx, but we know that this is simply minus ex cosine x, that's what you get, plus but when you integrate ex cosine x, what we get? We get ex sine x minus ex sine x dx, right? We substitute for that. So we substitute, so we put it here. Okay. So now what we can do, we can move the negative one to the other side. That means you're going to get twice ex sine x dx equal ex sine x minus cosine x. Okay. So now what do we do? We can divide both sides by 2. So we divide both sides by 2. Ex sine x dx is equal to 1/2 ex sine x minus cosine x plus, okay, let's add a c now. Okay, so let's add a c. So that is the answer. You can see that this problem is slightly different, but it's not too difficult, but it follows a different path. So you have to do 2 integrals, and from the second integral you will substitute the first integral. You do 2 integrals and then substitute. You're going to substitute for ex cosine x, and then what you do, you're going to move the integral to the other side again twice, and then you divide, and then you end up getting half ex sine x minus cosine x. Okay, this is a special integral. So I'm going to start here. We normally ask this question in the exams. Okay, so this is like common problem that we ask, and see how we did it. We had to do 2 integrals and then add them together. Okay, so that's good. So this is the end of the what we call the most important technique of Calc 2, what we call the integration by parts. Okay, that's the end. Thank you.